Question number 1. A study of pain relief to morphine and placebo in individuals with postoperative pain found that 3,024 patients who were told that they were receiving a stronger painkiller while receiving a saltwater injection found as much pain relief as 3,050 patients who received a dose of morphine. So is this description an observational study or an experiment? Explain. In this case, we would determine it to be an experiment because there is a treatment. And the treatment would be the morphine. And it's being compared to the placebo or the saltwater injection. So describe the population. So a population is the group that we are intending for our observational study or an experiment to describe. So it's really the intent of where we want to generalize the information. And so even though we have some detail about the patients who were receiving the morphine and placebo, we're assuming that the population is the group or the people who are experiencing post-op pain. The sample, on the other hand, is the more specific group that you've chosen. In this case, we could say it would be those 3,024 patients who received the painkiller, as well as those who received the morphine. So it's the total group. This would be the 6,074 patients participating in the experiment. When we want to describe the placebo, placebo would be considered the saltwater injection. The placebo effect in this case is that those patients who received the saltwater injection found just as much pain relief. The treatment group in this case would be the 3,050 patients who received the painkiller or the morphine. And the control group in this experiment would be the other group, or the 3,024 patients who received the salt water. The question as to whether the experiment was single blind or double blind is not necessarily clear in this case. We would assume that it is at least blind because the patients should not have been told whether they would be receiving salt water or morphine. In fact, it's important in a placebo that those patients not be told that information. So we know it's at least single blind. As far as double blind, we cannot tell if it's double blind based on the short description that we were given. In order to be double blind, then whoever was giving the injection, we assume a nurse or the doctor himself or herself would need to not know whether they were giving the salt water or whether they were giving the morphine. So again, we can only tell from this experiment description that it was single blind. Let's go on to our second question, which also involves collecting data and some vocabulary around it. Let's say an SLCC student wants to know if college students vote Democratic or Republican. So they ask their Math 1030 classmates to state who they are going to vote for U.S. President as well as Utah Governor. Question A, what kind of sampling method was used? Select the best description and justify your selection. So on your test, I won't force you to write all of the sampling methods. You do not have to have them memorized per se, but you do need to be able to select from a list. So simple random sampling, stratified sampling, quota sampling, cluster sampling, systematic sampling, and convenience sampling were all types of sampling that your book referred to. As a brief review of these types of sampling, a simple random sampling would be, just as it indicates, it is random. So if I put everyone's name in a hat and pulled out a name or so many names, that would be a random sample. Stratified sampling is that we have subgroups and that we are picking so many or randomly within those subgroups. Quota sampling is one where maybe we, an example of this would be, I know that Utah is, like 60% Republican and 30% Democrat. So I call people, I decide to call, people until I have 60 people who state that they're Republicans and 30 people who state that they're Democrats. And then I continue to call until I get my quota. A cluster sampling would be, it also has to do with that subgroups, but we are actually picking the entire subgroup. So I could say, hey, there are 2,000 classes being taught at Salt Lake Community College. And so I put those 2,000 classes into some kind of randomizer, and I pick 5 of those classes to go ask my questions to. So I ask 5 different classes, but I ask the entire subgroup. And then systematic sampling is every nth member, or I could, list the classes in alphabetical order or by like CRN or section number or something. And I just say, okay, I'm going to pick the 10th or the 100th class on this list. And that would be, or the 100th person or something. And then convenience sampling is about picking people or asking people or taking a sample from whatever's convenient to you, which is what's going on in this case, because they're asking their classmates about their affiliation, political affiliation. So it's very convenient to them. As far as the kind of sampling bias that you might see, let's briefly discuss those. So sampling bias just means that not everyone in the population has a chance of being picked. And so in this case, like what would be our population? They want to know or make inferences about college students. And so because I'm asking like SLCC, and in fact, not just all SLCC students or randomly picking SLC students, I'm picking people that are in my class. So that would definitely be considered a sampling bias. Voluntary response bias would be if I create a survey and I put it on a website and I say, please, answer this survey, but anyone could answer it and they could choose to answer or not answer. That would be a voluntary response. I don't know that I would consider this voluntary, although you could argue, whether the students are going to actually respond. It was not set up as a voluntary response bias. Self-interest study. This is, again, not necessarily the case here, but a self-interest study would be one in which like we know that this SLCC student is affiliated with either the Democratic or Republican Party, and they will often it's kind of sometimes tied to like loaded questions, like this is the reason why they're doing this. We don't have that information to make the determination that this was a self-interest study. Perceived lack of anonymity. So I would say in today's days, perceived lack of anonymity might be the case when we're talking about political affiliation. People might not want to tell the truth one way or another. Loaded questions, we can't necessarily tell from this survey. I wouldn't call it loaded if you're just saying, who are you going to vote for, right? If they stated the question as something like, you should, are you going to vote for Donald Trump, who is going to save the economy, or, Biden, who, has caused so much inflation, right? Like if you just added some load to those questions, then it would be considered a loaded question. And then the non-response bias would be people not answering at all. So that one you could argue could be there, but I probably would select the sampling bias and perceived lack of anonymity. And just to clarify, with the non-response bias, that would be something like if they just refuse to participate. We don't know whether that would occur with this survey or not. So it may or may not be chosen. If you do select non-response bias, you would need to explain why you're selecting it in the justification.
Suppose the city of Harriman has 58,000 registered voters. There are two candidates for city council in the upcoming election, Gardner and Orgill. The day before the election, a telephone poll of 250 randomly selected registered voters was conducted. 135 said they'd vote for Gardner, 97 said they'd vote for Orgill, and 18 were undecided. So question part I, or the first question is, give the sample statistic for the proportion of voters surveyed who said they'd vote for Gardner. So we're going to go up here. If they have voted for Gardner, then I'm going to pull that information from the 135. So 135 is the raw number of people that want to vote for Gardner, but you want to, of course, make this into a fraction. You want the statistic or out of how many possible voters. So we don't want to go to 58,000 because that's not the number that 135 was drawn from. Instead, it was drawn from the 250 people or registered voters that were randomly selected. So we're going to take 135 over 250. Now, this is where on the test you want to be careful and make sure you're following directions. It does ask you to write this as a simplified fraction. So if you have a calculator that will simplify your fraction, you're going to put 135 over 250. And that's going to give me 27 over 50. If you didn't have a fraction calculator, you would just, of course, divide by whatever the common factor is. So you could divide them both by 5. And so the sample statistic is 25 over 50. Sometimes we put statistics as fractions, sometimes percent, sometimes decimal. Of course, if you wanted a decimal, you take 27 divided by 50 and write that as a decimal. And if you wanted it as a percent, of course, you'd move it 2 places after changing it to a decimal. So part 2, how many of the 58,000 registered voters does the sample statistic suggest will vote for Gardner? And so because I left this as a fraction, I'm going to go ahead and set it up as a proportion. So going back to what we learned about in module 1, you can set up a proportion. If basically 27 out of every 50 people plan on voting for Gardner, you want to know how many out of 58,000 voters. So we can do this by cross multiplying. I'm going to take 27 multiplied by 58,000. That's going to be equal to 50 times by the x. So I'm taking my calculator, 27 times 58,000. That's 1,566,000. And we're going to divide that by 50, of course, to solve for my numerator. So if I divide that by 50, I'm expecting 31,320 voters. Okay, Let's move on to, you are given a table, a frequency table to be more precise. And for the first part, it's asking you for the mean, or in other words, the average, what we typically think of as average, cups per day for the class. Because this is given to me as a table, I have to interpret what this means. So basically, one person drinks no cups of water per day. So I could say, that there would be someone who said 0 cups, and basically 3 people drink 1 cup per day. So if I wrote that out as far as cups of water per day, I would have 3 ones, and I would have 5 twos, etc. Right? And like if I was asking for the median, you don't want to necessarily have to write these all out and find the middle number. So we will do that in just a little bit, finding the median. But to find the average, we want to basically multiply to get the sum of each column, and then add them together. And then we're going to divide by the, it's a little symbol for sum, the sum or the frequency. So I'm going to take 0 times by 1 plus 1 times by 3 plus 2 times by 5 plus 3 times by 4 plus 4 times by 8 plus 5 times by 3 plus 6 times by 3, etc. 7 times by 2. So it's a long one. 8 times by 0. By the way, you wouldn't even have to do that if you're going to use the 0, because it will, of course, equal 0. And when you add 0 to anything, you get the same thing. And then I'm going to add up my frequency: 1 plus 3 plus 5 plus 4 plus 8 plus 3 plus 3 plus 2 plus 0 plus 1. And I get 30 people. So there were 30 people in the class. And for the sake of time, I will put the answer in the key, but that's how you would find it. To find the 5-number summary. So a few of you guys struggled a little bit to find Q1 and Q3 on your last project about the magnets and pain. So I do want to definitely hit how to find Q1 and Q3 mathematically on a test. So let's talk about, first of all, the first number, which is your minimum. And that would be the minimum number that appears. In this case, it would be 0. So somebody had 0 cups of water per day. And then let's just jump over to the max, which would be 9. Okay, so someone mentioned that they drink 9 cups per day. So that's going to be your max. Just write that. Now, to find Q1 and Q3 and also the median. So Q1, think about Q as in quarter. So the first quarter would be 0.25. If you think of a quarter, it's 25 cents. If you think of the third quarter or 3 quarters, it's 75 cents. And the middle of those two, or the median, is half. So what I'm going to do is take 0.25 times by the frequency. Okay. And I'm going to do that for each of the Q1, the median, and Q3, or how many people did I ask? Okay, which would be 30. So for Q1, I'm going to take 0.25 and I'm going to multiply it by 30. So 0.25 and I times it by 30, I'm going to get 7.5. Now, this is where some of you guys made a mistake. So 7.5, anytime you have a decimal, that means even if it was a 0.1, whether it's 0.5 or 0.1 or 0.01, you're going to round it to the next value. Okay, so don't think about typical rounding rules. Instead, just always round to the next value. So I'm going to round this to 8 or look for the 8th value in my data set. Okay, now to find the 8th value, you're going to think about adding up the frequencies along the bottom of the table. So the first value is a 0. The 4th value, okay, 1 plus the 3, or the 4th value is a 1. So basically the 2nd through the 4th values are 1s. And then the 5th through the, if I add my 5 to the 4th value, the 5th through the 9th values are all 2s. So the 8th value has got to be a 2. Okay, let's go through that again, but with the median, and then we'll do it again with the Q3. So median, think 0.5. You're going to times that by, there were 30 people asked, so that's 15. Now, if it's whole, that doesn't mean we use the 15th value. Okay, so if it's whole, what I end up doing is taking the 15 plus the next value, and then we're averaging it. Okay, so I'm going to take the 15th and the 16th value. So we've got 4 more here. So this is the 10th up until the 13th value. And then 8 more beyond the 13th is 21st value. Okay, so that means the 15th value, or basically the 14th through the 21st value, are all 4s. So if the 15th and the 16th value were different, I would add them up and divide by 2. You can still do that if they're the same, but you'll see here it is kind of silly to do that. What's in between a 4 and a 4? Well, a 4. Okay, so the median is going to be a 4. Now on to Q3. Q3, think of that 75 cents for the 3rd quarter, or 3 quarters. You're going to take 0.75 times by 30. That gives me 22.5. Again, because this is a decimal, I'm going to go to the next value. Okay, so that's my thought bubble there. So I'm going to look for the 23rd data point. Okay, so I'm going to just keep going here. Looking at, I'm already to the 21st, add 3 more. That's going to take me everything up until the 24th. So the 22nd through the 24th values are 5s. So the 23rd value is going to be a 5. Anyway, I hope that helps with determining Q1 and Q3 as well as the median. So the exam scores for a test that include both math and physics is shown below. If Anita received 82% on the math portion, what percent of students scored higher on the math portion than she did? Okay, so let's look at math portion. So there's my clue, meaning I'm going to look in this middle box plot for mathematics. Let's go up until there's an 82. And so Anita is sitting at the top of a box. And so what this question is doing is asking you, can you interpret what box plots mean? And so when we drew box plots on our last project, we drew them horizontally, but you certainly can draw them vertically as well. So since Anita is closer to the end than she is the low end, she's closer to the higher end, what we want to know is this is basically the lowest or the minimum. Okay, Q1, Q2, Q3, And then the maximum, there's your 5-number summary, is just all along each box or each part of the box plot, I should say. So Anita is sitting at Q3, which means, remember, 3/4 is 75%. So 75% scored lower than her. Got to be careful on this one because it actually asked how many scored higher than her. And so we want to think about, well, if 75% scored lower, to figure out how many scored higher, I'm going to take 100% minus that 75%. Or in other words, 25% of the students scored better than she did on the exam. Okay. And looking at LaShonda, if LaShonda scored a 35% on physics, so now I'm going to look at the physics box plot. And 35%, so looking along the left-hand vertical axis, 35% is down at the bottom of the box. Okay, so that would be Q1, or 35% for physics. So let's look at what percent of students scored lower than. So we want to know what percent are down here. And because it's Q1, it would be 25%. All right, moving on. We're going to talk about probability here. Let me just mention on this one, even though I have this on the practice exam or review, I don't usually ask these questions on an exam unless I give you a picture, similar to when you did the exercises, because I don't assume that a lot of you guys know face cards as well as maybe I do, or someone else who plays cards does. So this is an example of finding probability, but again, we would give you probably something more like the marbles, pulling out a green marble versus a red marble, or something a little more specific where you are given numbers. So standard deck, let's just review real quick, or help you understand. The standard deck has 52 cards. There are 4 suits. And so there are 13 cards in each suit. So everything from a 2, 3, 4, 5, 6, 7, 8, 9, 10, and then Jack, Kings, Queen. And we generally don't include jokers, but find the probability of drawing a king and an ace. Okay, so this one's kind of a silly question. I'm thinking about what I would put as the answer here. If I draw one card, maybe it's not so silly. It's got to be a king and an ace at the same time. So you've got 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Okay, so there's my 13 cards. So, oh, an ace. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, there's my 13 types of cards. So can I draw a king and an ace at the same time? No. So yeah, a silly question. So there's a probability of 0 for one single card. What's the probability of drawing a spade and a face card? So these are considered faces. A jack, a queen, and a king. If you had the cards in front of you, you would literally see faces on them, like people. And so those are considered faces. So spade is a suit. And so there would be a jack, a queen, a king, that all are spades. So there's 3 face cards out of the deck of 52. So you would say, in order for there to be both spade and face, okay, I would have 3 of those out of the 52 cards. Find the probability of drawing a king or an ace. And so this is where it would be helpful. I'm not going to pull up. If you have the picture in front of you, that might be helpful. It would take me too long to draw it all out. But if I have a king, that's a suit, right? So there are 13, sorry, there are 4. I said that all wrong. King's not a suit. It's a type. The ace is a suit. Okay, and so there are, well, we're going to start all over there. A king or an ace. Okay. Find the probability of drawing a king or an ace. So that goes back to that first question. The first question was an and, but this one I'm asking an or. And so it's possible to draw a king or an ace. There are 4 kings and there are 4 aces in the deck. And so the probability of drawing one or the other, we would add those 2 together, or 8 out of 52. And we could reduce that. We should usually reduce our probabilities. So I'm going to divide those both by 2. That's going to be 4 out of 26. Or basically divide by 2 again, which would be 2 out of 13. Part D, find the probability of drawing a spade or a face card. So the spade is a suit. It's kind of looks like an upside down heart with a little tail. Or a face card. And so this is where there's some overlap. If we think about it like a Venn diagram, there are 13 spade cards. Upside down heart with a little tail. And there are some face cards. There are 3 face cards in each suit. So there are basically 12 faces. But we want to know how many are between those. Okay, so we can't just add the 13 and the 12 faces, because there are a few of those cards that are both, and so we have to subtract out what are both. So there would be a jack of spades, and there would be a queen of spades, and there would be a king of spades that would be both a face card, and I should probably draw those in black, but you get the idea. There are 3 cards that are both of those. And so to figure out an or statement, we would say that we have 13 out of 52 for the, basically what we would write mathematically is the probability of spade, plus the probability of a face card would be 12 out of 52, but we're going to subtract the probability of being both a spade and a face, excuse me. So we're going to subtract out the 3 that are both. So 13 plus 12 is 25, minus 3 is going to be equal to 22 out of 52. Notice I don't reduce until the end. I like that to keep that denominator 52, and that would be 11 out of 26. Answer the following probability questions. If we roll 2 die, one at a time, are the rolls dependent or independent? So this is kind of an understanding vocabulary question. What does independent versus dependent mean? So I like to think about independent, like one doesn't affect the other. Dependent means one does have an impact on the other. Like if I take a card out of the deck, now I have 51 less cards to draw from. So my probability of drawing the same card again goes way, it changes, right? So in this case, because it's dice, it would be independent. And so you would explain that as, I'm not going to take the time to do that, put it on the key, but basically independent because one doesn't impact the other. If we roll the 2 die as described, find the probability of getting a sum. So I like to think about how can I get a sum of 12. So on a dice, I could have a 6 on one of them and a 6 on the other, right? And that would give me a sum of 12. So you could put that as 6, 6. Okay. But we also have, do we have any other ways of getting a 12? Could you get 4 on one and 8 on the other? Well, not if you understand a die, which only has 6 sides, right? And so the max you can have on a side would be 6. And so there's only, you must get a 6 on one and a 6 on the other. So the probability of getting a 6 is 1 in 6. And we're going to multiply that because it's independent by the chance of getting another 6, which is 1 in 6. And so the probability of getting a sum of 12 would be 1 in only every 36 rolls. Again, on average, in the law of big numbers. Okay. If we roll the 2 die as described above, find the probability of getting 2 even numbers. So we want to find the probability of getting an even number on the first die, and then the probability of getting another even number. So the probability of getting an even number, if we think about even, it's 2, 4, 6 on a dice. So that's 3 in 6, and then another 3 in 6. We could reduce those before we multiply. It's 1/2 times by 1/2, which would be 1 in 4. So the chance of getting 2 even numbers is, we'll leave it as that fraction.
You pack a suitcase for an extended vacation, and in your suitcase you have 10 pairs of socks, 6 of which are white, and you also have 7 t-shirts, 3 of which are white. If you reach in and randomly grab a pair of socks and a t-shirt, what's the probability that both are white? So this one involves an or statement. And so we could, you could go to your formula sheet and review that, but the probability of event A or B would be equal to adding the 2 individual probabilities and then subtracting off the overlap of 27 over 35. Moving on to number 9. So if you purchase a box of goodies for trick-or-treaters, and the box contains 40 packs of goodies with 10 each of the following. So you have 10 Nutter Butters, 10 Oreo packages, 10 Nilla wafers, and 10 Chips Ahoy. If you mix the goodies in your basket and 3 trick-or-treaters come to the door and grab from your bag without looking, I don't know who does that, but they just grab in there and get one. What's the chance or probability that all 3 trick-or-treaters will randomly grab Nutter Butters? So this is a conditional probability. So we're going to, if I want the probability of all 3 to choose Nutter Butter, and I'm just going to abbreviate that NB, then what's happening is it would be equal to the probability of the first one getting Nutter Butter. But because this is a dependent event, we're going to multiply it by, so the second person would draw out, from this bag, and you want them to get a Nutter Butter, given that the first one already chose a Nutter Butter. So if I want all 3 to get Nutter Butter, that's the probability I'm trying to calculate. Then the second one is Nutter Butter given Nutter Butter. And then the third one would be Nutter Butter given that I have given away 2 Nutter Butters previously. So the first probability of getting a Nutter Butter for the first one who comes and grabs would be 10 out of the 40. However, when you get to the second person grabbing, now I have 39 treats in my bag and only 9 of them are Nutter Butters. And then for the third person, we have 38 treats in the bag and only 8 of them are Nutter Butters. Let's go ahead and put this into our calculator and calculate the probability. So the probability would be 3 in 247. That being said, if I read my instructions, which you should always read them very carefully, it did say to write the probability as a percent, rounding to the nearest whole number. So there's a couple ways we can change this to a percent. We can first divide to change it to a decimal, which would be 0.0121 with some other numbers there. But rounding that to a percent, we're going to times by 100, which would be 1.2%. It did say round to the nearest whole number, so I would indicate that that is approximately 1%. So there's only a 1% chance, if they were really choosing randomly, that all 3 people would get a Nutter Butter.
A test was given to a group of students. The grades and gender are summarized below. If one student is chosen at random from those who took the test, part 1, find the probability that the student was female or got a B. And so with an or statement, you want to think about all, one or the other. So the probability that they're female, just change it, we'll change it, yeah, is 37, right? So 37 females out of, a group of 61. So that's the probability that they're female, right? What's the probability that a student gets a B? Well, for that, I'm going to look down the B list or column, and there are 24 out of, again, your total 61. So if I had asked what's the probability of being female, you would say 37 out of 61. What's the probability of drawing of someone who got a B? You'd say 24 out of 61. This is similar to our question on the face cards, okay, where there's an overlap. So if there's an overlap, we have to subtract out the overlap. So we're going to add those two together, but subtract out the probability that they're female and have a B. So if we look at our female row and our B column, we see the overlap is 11. So I'm going to subtract out 11 of those students. Okay, so I'm going to get 37 plus 24 minus 11, or in other words, I get 50 out of 61. Okay, which again, I would accept if a question like this, I would accept either a fraction or a decimal unless I've told you otherwise, although I like fractions. All right, what's the probability of male and C? If I'm asking for an and, I want to think about, this is where I only consider the overlap. Okay, so let me erase my colors here. What's the probability that I draw a student who is both male and got a C in the class? And so I'm going to look for the row of male and C. And that's it. That's my numerator. So I'm going to put 4 out of 61. So, and is only the overlap or includes everything, take off the overlap. Part 3, what's the probability of A given that the student is female? So we have to understand, first of all, how to read this. So what's the probability basically that they received an A? Given, that straight line means given that they were a female. I like to think about this straight line as basically a numerator and a denominator. And so the female is going to be, or the number of females, I like to think about it like that. The number of females is going to be my bottom denominator. So I'm going to go up and look for how many females there were. And so I see there were 37 looking along female. There were 37 total. And then I'm looking only at that row and I'm looking for the number of A's. And so on that row, there are 14 students who got an A. So there are 14 out of the 37 female students who got an A. And then reduce, if possible, 37 and 14 don't have a common factor. So average.
Let's talk about the probability of finding at least one. In this case, we are given that the probability that a random student in math doesn't complete their online homework is 15%. So if I were to write that first sentence in math notation, I might write something like the probability, and instead of using all of the language that they don't complete their online homework on time, I might just say the probability that they're going to be late is 15%, or we can write that as a decimal, 1500ths. The next question asks, what is the probability that the student will not complete at least one of their last 5 homework assignments on time? So what is that asking? It's asking the probability that at least one of their last 5 assignments was not on time. In other words, the probability that at least one of the 5 assignments will be late. To find the probability that at least one of the 5 assignments is going to be late, we're going to use the complement. So I'm going to take 1 minus the probability that this does not happen. So if I think about it, what would it look like to have at least one of the 5 assignments late? Well, that means that anytime if I had 5 different assignments, as long as one of them was late, the others could be, if I used O for on time, it doesn't matter where that L is, as long as it's anywhere and I can have more than one anywhere, then it would meet this condition, right? So the only time that it doesn't meet this condition is if they were all on time. So if I can find the chance that they're all on time, if I subtract that from 1, I will be able to figure out the probability that at least one is late. So let's talk about the probability of one being on time. And so if the probability of being late is 0.15, the probability of being on time is going to be the complement of that, or 85%. So the probability of being on time is 85%, so the probability of 5 being on time would be the probability of being on time to the 5th power. So I'm going to take 1 minus the probability of being on time to the 5th power. So that's 1 minus 0.85 to the 5th power. Entering this into my calculator, 1 subtract 85% to the fifth, 6, 2, 9, 4, etc. If I'm asked to round that to the nearest tenth of a percent, I'm going to move it 2 places to change it to a percent. And then the 1 place after that is going to stay a 6. So the chance that a student will not complete at least one of their last 5 online assignments, again, assuming that these are independent events, would be 55.6%. Let's move on to a Bayes theorem problem. Assuming that breast cancer has an incidence rate of 0.4%, or 4 in 1,000, and reports indicate that the diagnostic test or mammogram used to detect the cancer is accurate 87% of the time for women who have breast cancer, and a false positive of 10%, meaning 10% of the women are told they have an anomaly and return for further testing. We're going to fill out this two-way table, assuming that the total is 10,000. Let's take this question one step at a time. The first step is to determine how many of the 10,000 people that were tested would actually have the disease. So that is related to our incidence rate, or the 0.4%. To figure out how many of these 10,000 women would have the disease, we're going to take 0.4%, or as a decimal 0.004, and multiply it by 10,000. This will give us 40 women who would have the disease in a random set of 10,000 women. Once we have that number, we could figure out how many people wouldn't have the disease by subtracting the 10,000 minus 40 to give us 9,960 women who we would assume not to have the disease. Let's go on to our next percentage given. So the next percentage is the 87. So if we read this sentence carefully, we read that the test used to detect cancer is accurate. Okay, that's what we want. 87% of the time for women who have breast cancer. So that means that they have the disease assumed to be breast cancer, and that it would be positive. So we're going to put our 87% into that box, but I need to multiply it by the number of women who actually have the disease. So it's given that they have the disease that they would test positive. So that would be multiplied by 40. So we're going to take 87% multiplied by 40 to give us 34.8. By the way, we will not round this to a whole number, even though when we talk about women, we wouldn't talk about 0.8 of a woman, because we're going to find probabilities, and so we want this to be as accurate as possible. We don't always have exactly 10,000, so we're going to generalize this and therefore keep the decimal in our cell. Moving on to the next percentage that we were given, the 10% is a false positive rate. That means that I'm looking again in the positive category, given that it's positive, but we don't want that to occur, false. So we don't want them to have the disease if they test positive, right? So that's where our 10% is going to go. And again, I need to multiply that 10% by the number of people who do not have the disease. In this case, we're assuming it to be 9,960. If I multiply 10% by 9,960, I'm going to get 996. From here, we can fill in the rest of the table just using addition or subtraction. Because the total has to equal 40 on that top row, we're going to end up with 5.2 in the negative with disease, and subtract 9,960 minus 996 to get 8,964. We can add the negative diseased and negative no disease to get 8,969.2. And we can subtract that from 10,000 to get our first total for the total positive, or we can add that column and we end up with 1,030.8. Next, let's answer the questions regarding probability. So the first, or part B, says find the probability of B. I might state this as just finding the probability of a positive test result. So that would be equal to the number of positive test results given in that first column divided by the total of 10,000. When we divide this on our calculator, we get 1,0308, or rounded to the nearest tenth of a percent is 10.3%. So the chance of having a positive test result will occur 10% or 10.3% of the time. The chance of not having B, or not having a positive test, which we can also write mathematically with a line over the B, would be the complement of that. So we could take 100% minus the 10.3% would be 89.7%. Again, rounded to the nearest tenth of a percent. Let's move on to the probability of A given B. Again, this could be stated. The probability A is the disease, or in this case, we could be even more specific, breast cancer, given B, or that they test positive. So what's the chance that a woman would have breast cancer given that they tested positive? We always want to start with the given, the total number in the given. So I'm going to think about the number that tests positive, which would be our total in the column of positive, or 1,030.8. And then the numerator is going to be the number who have breast cancer, again, given that they tested positive. Okay, so you're going to look in that column. The number that have breast cancer in that column would be 34.8. We're going to go ahead and divide 34.8 by 1,030.8. We would get a decimal approximation of 0.03376, which we would round. If I am still asking for a tenth of a percent, I would say it's about a 3.4% chance. Again, if a woman tests positive, the chance of her having breast cancer is actually very, very low. So this would be something the doctor would definitely want to tell the patient. Just because you tested positive does not mean you have breast cancer, which is why they will send them in for more analysis using different tests. Next, what is the probability of not A given B? There's two ways to find this. We could actually use a complement, or if I did this using the chart above, I would say, again, the number on the bottom is going to be the total in the column of B, or 1,030.8, and the numerator is those that we assume not to have breast cancer, which would be the 996. If we divide that, what we'll find is that it will be the complement, which would have been 100% minus the 3.4%, or 96.6%.
Suppose an AC manufacturing company estimates 3% of their AC units will fail after the original warranty period, but within 2 years of purchase. The average replacement cost is $2,000. I think that's actually pretty low, but maybe that's the repair cost. They offer customers a 2-year extended warranty for $179. What is their expected value for each warranty? The expected value looks super, super confusing, but it's actually, I like the second formula. It's the value, basically, of option 1. You can even think about that as option 1, or they call it outcome 1, times by the probability, plus the value of opportunity 2, or outcome 2, times the probability. And then however many ways that this can be thought of. So when we go back up to this question, basically, how many things can happen? Well, we actually only have 2 outcomes. So either the AC unit fails or it doesn't fail, right? So those are your 2 outcomes. What we call outcomes. And so what I want to do is figure out what happens money-wise, okay, if it fails. So let's talk about fails and not fails, which we can put a line over the top, means do not fail, okay? So value-wise, if it fails, and this is to Frigidaire, what happens? So if it fails, they may lose $2,000. Okay, if it doesn't fail, okay, then if they have a warranty, then they just made $179. Okay, so that's what we would think happens. However, even though it fails, if the consumer did put a warranty on it, which is what we're asking, is when they get a warranty, what kind of money will they be making or losing? They lose $2,000, but they actually still gained the $179, if that makes sense. So because they got that up front, and then they're going to have to spend $2,000. So that's the value if it fails, and if it doesn't fail, then they earned $179. And then we want to talk about what's the probability of it failing. So the probability of it failing is 3%. I'm going to write that as a decimal. And the probability, I'm kind of just creating a little chart here, but the probability that it doesn't fail is going to be 100% minus off the 3%. So in other words, 97% of the time, if 3% it fails, because it can only fail or not fail, 97% of the time it's not going to fail. Okay, and what we're going to do is we're going to multiply those. So the expected value is going to be negative 2,000 plus the 179 times by 3% plus a gain of $179 if it doesn't fail, which has a probability of 97%. Okay, and I'll put the answer to this up in the key. How much should they expect to make or lose if they sell 10,000? What we're going to do is take our answer from A and we're going to multiply it by 10,000, because that's how much, the answer to A is how much they're going to be making, again, on which expected value, law of big numbers for every 1 unit, and then multiply it by 10,000.